Hello and welcome. In this video, we're going to talk about some of the compare and math functions that are embedded within RsLogix 500. As part of the math and compare functions, SLC processors support a range of data handling and manipulation instructions. So you can do things like move data from one register to another, move a static value into a register. You can manipulate data with math functions using add, subtract, multiply, divide, square root, etc. Or you can do comparisons like greater than or equal to, less than or equal to, equal to. And so first we're going to talk about comparison instructions. And a comparison instruction is just simply a instruction that tests the relationship between two different values. So you have a source A, which is an address, and then source B is an address or a constant value. And when the comparison evaluates to true, the output of the function also executes to true. So you can attach that to things like OTEs to indicate status of a comparison instruction, or you can use it to activate logic further on in your sequence. So the first one we'll talk about is the equal to instruction. And this instruction just simply tests whether two values are equal to each other. All right, so first thing we want to do is open a few programs before we open RsLogix MicroStarter Lite. So the first one I'm going to open is RsLinks. And then next I'm going to open the Emulate 500 program. And we'll go ahead and minimize both of these for now. And then we're going to open RsLogix Micro. And in Links, we just want to make sure that we have our Emulate 500 emulator running. And we're going to start a new project to demonstrate the comparison function. So we'll just call this ML1100 for the PLC name. Processor node is, we'll do 0, click OK. And then we're going to add an equal instruction. There are several different ways to add the equal to instruction to your rung, but probably the easiest and most common way is by going to the compare tab of the instruction set and clicking on the EQU symbol. That will add the equal to instruction. And we're going to use in70 for source A. And we'll call this value A, and we'll just use A for the symbol. And then for our source B, we're going to use the next available integer, which is in71, and we'll call this value B with B as the symbol. Next, we want some indication that this is evaluating as true. So we're going to attach a output to energize instruction at the end of the equal instruction. And the way that this will work is when the comparison instruction evaluates as true, the output of the instruction will also execute as true, providing continuity on the rung to our output to energize. So we'll give this output to energize an internal bit address, which is B300, and we'll just call this equal true, and we'll do ET for the symbol. Next, we want to verify our rung, make sure we have no errors, and then we're going to save our project, and we'll just accept the defaults here. We're just doing this for demonstration, so the name doesn't matter. And then we're going to download to the controller and go online. And lastly, we need to place our controller in run mode so that we can start testing our equal to instruction. So in the default state, the integer value on address 0 is 0, and the integer value on address 1 is also 0. So right now, the output of this instruction is true because both of our integers are equal to the same number. So if I were to change in70 to a different value, 200, for example, our output goes false, and therefore our bit B300 also goes false. So the next instruction that we're going to talk about is the not equal to instruction, and this operates as the inverse of the previous instruction, and it tests whether two values are not equal to each other. And the way that this instruction works is that when both values are not equal to each other, then the output is true. If they become equal to each other, like in this example, we have in70 set to 12, and we're comparing it against a static value of 12. So those values are equal to each other, and therefore our output is false. So we'll switch over to RsLogix 500 and we'll demonstrate this instruction. All right, so in this demonstration, I'm going to demonstrate the not equal to instruction. I'm also going to add a couple additional instructions because there's a specific challenge that you might face when trying to add multiple comparison instructions and using the integer registers. So one of the issues that you may run into is that the integer table by default only has 2 registers that are available. So we're going to increase the number of elements in our data table. So we'll increase this to 50 to ensure that we have enough registers to show examples of a variety of different comparison instructions. So we'll click apply, click OK. So now if I click on the integer data table, you can see that I have some additional registers, and I go all the way up to N7:49. So it starts at N7:0, ends at N7:49. So we bumped it up to 50, and now we can use those registers in our comparison instructions. So we're going to add a few comparison instructions. First, we'll do our equal to once again by clicking on the equal. Next, we're going to add the not equal to. Then we're going to add a less than, Next, we'll add a greater than, and then we're going to add a less than or equal to, and a greater than or equal to. So now we have equal to, not equal to, less than, greater than, less than or equal to, and greater than or equal to. So for our first one, we're going to use the first available integer register, which is N70, and we'll call this input 1, and we'll just give it I1 for the symbol. Then we're going to use N71 for source B, and we'll call this input 2. Next, we're going to use N72 for our not equal comparison, and we'll call this input 3. Then we'll use N73, input 4, N74, input 5, N75, input 6, N76, input 7. Then for our source B, we'll use N77. We'll call that input 8. Next, we're going to use N78 on our less than or equal to. That will be input 9. Then N79 is input 10. Then N710, which is input 11. And lastly, N711, which is input 12. All right, so then we want to validate our outputs of each of these instructions using a series of bits. So we'll use the B3 data register, and we'll just do these in order. So we'll use B30, and I'm just going to leave the description blank on these for the sake of time. We'll do B302, B303, B304, and lastly, B305. All right, so we have all of our major comparison instructions. We're going to verify our rung, make sure that we don't have any errors. And then we're going to save our project as comparison master. Then we're going to go online with the download. And we're going to place the processor in run mode so that we can start testing each one of these equations. So currently we have a few that are by default true. And the reason for that is every integer value initializes to 0 unless otherwise stated. And so we have a few that meet the criteria of equal to. So in the less than or equal to, 0 is less than or equal to 0. And in the greater than or equal to, 0 is greater than or equal to 0. And also in our equal to instruction, 0 is equal to 0. So we'll just go through and change these values. If I change that to 12, then B30/0 goes false. On the not equal to, if I change this to 5, our B30/1 goes true because this is no longer equal to the value at N73. Next, we're going to use a value that's less than a value on N75. So we'll keep N74 at 0 and we'll bump N75 up to 10. And we can see our B30/2-bit goes true. Next, we're going to test a greater than value. So we put a value that is greater than the value on N77. So we use 10. And so now 10 is greater than 0. So our output on B30/3 goes true. Next, we're going to use a value on N78 that's less than the value on N79. So we're going to increase N79 to 10. And now our value at N78 of 0 is less than our value at N79 of 10. And then lastly, we are going to enter a value on N711 that is greater than N710 so that our instruction goes false. And so now our value is less than the value at N711 of 5. Now if we increase this to 10, our output will go true and our bit at B305 will also go true. So to summarize the instructions that we just demonstrated, we use the less than instruction that tests when one value is less than another. We also used a less than or equal to instruction that tests if a value is less than or equal to the value at source B. We tested the greater than instruction that tests whether a value is greater than the value on source B. So in this example, we have N72 set to a value of 12, and 12 is greater than the value of 10 at source B. Then we tested the greater than or equal to instruction, and that will test whether a value is greater than or equal to the value at source B. So in this example, our value of 12 is equal to the static value of 12 on source B. All right, thank you for watching, and I hope this helps.